Welcome you all. We are trying to understand tensile testing of textiles. In this current lecture, we will try to understand the various factors that affect the tensile test and the principles behind the instrument in which the tensile test is being performed. So these are the list of factors that influence the tensile test. As already mentioned in the previous lectures, tensile test is the test performed by applying the force along the axial direction of the material. So usually textile materials are subjected to tensile load, and when you are performing a test in for any fiber or yarn or fabric, there are many factors that influence. So the while performing the test, you have to be very careful. So the first and the foremost factor in influencing the tensile test is the principle behind which the tensile test instrument works. There are various principles how a load is applied or how a material is extended. When you apply load, the material extends. When you extend, there is a stress created in the specimen. So either way, it may happen. So how you apply the force to that or load to the material and how it elongates. The basis on which the instrument performs the test is called the principle behind the instrument. So we will see the principles behind it in the later stage. Now, the second thing is the specimen length. How long the specimen you take. So very short fiber or a long fiber, short yarn or a long yarn, short fabric or a long fabric. So according to the length of the specimen, the reading that you get will vary. We already saw on weak link effect. The longer the gauge length is the distance between the two jaws. The longer the gauge length, the longer will be the specimen length. If the specimen length is higher or the gauge length is higher, there will be more weak links. There will be probability of there is a probability that there will be more weak links when there is a longer specimen length. So it is bound that you will have a lower strength reading. So you have to be very careful while assigning a specimen length, and they have standardized the specimen length for a particular type of test. Say it is 300 for a yarn for a single yarn strength. For single fiber strength, it is lesser. For fabric, it is say 12 inches. For the type, according to the type of test, it varies. So the next is the rate of extension. You keep one jaw fixed and the other jaw you are moving. The speed at which this jaw moves, if the top jaw is fixed, then the extension that you apply to the sample, you may extend this very slowly or very fast. So this rate, speed at which rate means mm per minute, mm per second. So that rate at which you extend the sample has an influence on the tensile test. And the time to break. So if you have a higher rate of extension, then the time to break will be lesser. So again, next is the rate of loading. How fast you add the load. It is 1 kg or 1 kg per second or 10 kg per second. For every second you add on 10 kgs or 1 kg or 500 grams. How much load you apply to that sample. You're not keeping on the material. It is that you have the material and at the bottom you have the load that is applied. So if you increase the rate of loading, then again the time to break will reduce. So this has an influence on your tensile test. Then the capacity of the machine. Say if you are going and standing on, all of you would have seen a balance. Will you go stand on that balance and weigh your body? No, you can't do that. Or will you go stand if you want to weigh yourself? You go place yourself on a balance in which you weigh the fiber? No, you can't do that. Then again, if you go to you have seen weigh bridges. A lorry will go and stand, and they will find the weight of the material that is there in the lorry in weighbridge. You would have seen on the roads. So if you go stand on the weighbridge, and there will be no change. So the capacity of the machine is an important factor in the tensile test and the previous history of the sample. Again, already if you have strained and then again you perform the test, if it has not broken but you have strained the material, and again if you come and keep the material and test, it will show a different result. So these are all the factors. So if it should be constant for the various materials which you compare, or within for testing a sample, you have to standardize these things before performing the test, because all these have an influence on the tensile test results. So let us see one by one. So there are first one, the principles behind the. So there is a spelling mistake here. So it is here. There is a spelling mistake. I want you to TENSILE. So you have tensile test. So the principles behind tensile test, there are three types of principles. One is constant rate of extension, that is more commonly used principle behind most of the instruments. Uh, then constant rate of loading CRL, then constant rate of traverse CRT. So CRE, CRL and CRT. This principle is not only for textiles. Any tensile testing instrument should work in any of these principles. Not only tensile test instruments for which textile materials can be tested. It is an universal instrument, because tensile means application of load and acceleration. You can apply the tensile load for and perform tensile test for any of the materials available, like plastics, metals, bricks, anything you can do a tensile test. So it is common, the principles are common, and the common instrument used in anywhere, whether you test it for a brick or a stone or a plastic material or a metal, anything you test, the most common principle is CRE, constant rate of extension or constant rate of elongation. The specimen elongation is maintained at a constant rate. So the rate of increase in specimen length. So increase in specimen length. You increase the length. Say it is very common. One you tie so to understand CRE, you have take a rope, tie a rope to a fixture, say a pillar, and on the other end you tie it to a bike end, and the bike is moved at some speed, say 20 kilometers per hour. At a constant speed, if you maintain, then the increase in the length of the specimen is 10 kilometers per hour, say, or 20 kilometer, whatever you drive, that is the increase in length is 20 kilometers per hour. Similarly, so I hope you have understood what is the speed. So one end is fixed and the other end, one end is fixed and the other end is moved at a constant speed. So usually the speed is 300 mm per minute for a yarn test, and single for a single yarn test, and also for a lead test the speed is maintained. So the increase in specimen length is uniform with time. So every after 1 minute, your specimen length plus 300 mm. Second minute, after at the end of 2 minutes, your specimen length plus 600 mm. So this will be the change in length in the specimen that you are testing. So that is CRE principle. Next is constant rate of loading. The rate of increase in load is uniform with time. So for you to say it is 1 kg per second. So at the end of 1 second, you will see. I hope I told it as 1 kg per second. So the increase in load is uniform. You apply it. So you tie like this. At the bottom you have a weight. You add 1 kg per second. For each kg you increase 1 kgs. It is not physically adding like this. Just for an understanding, I'm telling you have a mechanism for increasing the load. So uniformly it is increased. So at the end, or after 1 second, the weight will be 1 kg. After 2 seconds, 2 kg, 3 seconds, 3 kg, 4 seconds, 4 kg, 5 seconds, 5 kg, 6 seconds, 6 kg, 7 seconds, 7 kg. So uniformly you are applying the load. So this, but the extension will happen, but it will not be at a uniform rate. When there is CRL, you cannot have CRE. Based on the type of this restraint characteristics of the material, the extension will happen. Similarly, when you have CRE principle, when the specimen is extended at an increase in the specimen length is at a constant rate, then there will be loading will happen. Then, but it may not be at a constant rate. Either CRE will be constant or CRL may be constant. So these are the two important principles, and the next one principle is CRT. In this, you have a top jaw, you have two jaws. The top jaw may be hanging. It is not fixed, it is hanging, and so there may be slight change in its position. So when you when you move the bottom jaw at a constant rate, the specimen extension will not be constant. Neither loading will be constant nor extension will be constant. So this type, just the bottom jaw traverses at a constant rate, so it is called as constant rate of traverse. So one clamp is moved at a uniform rate, whereas the other clamp is not fixed. Okay, so this type is called as constant rate of traverse. It is not that happening to the specimen. In the first one, CRE, the rate of extension of the sample is maintained constant. In the second type, CRL, the rate of loading the sample is maintained constant. Whereas here, neither constant rate of extension is maintained nor constant rate of loading. You don't have both. Just the bottom jaw moves at a constant rate. So that is called a CRT principle. These are the three principles behind which a tensile testing instrument works. So we'll go to the next factor affecting specimen length. We have already seen this in detail when explaining the weak link effect. As the gauge length increases, the breaking. As the gauge length increases, breaking strength decreases due to weak. This is not a link; it is weak link effect due to irregularity in the textile materials. So this is because of the irregularity in the materials. The next is rate of extension and time to bake. Increase in the breaking load, there will be an increase in the breaking load with increased rate of extension. If you increase the speed, the actual load may not be perceived by the instrument as and not perceived by the sample, because our materials are viscoelastic in nature. It is not truly elastic, it is not truly plastic, it is viscoelastic in nature. So it will behave differently for the rate of various rates of extension. So there will be an increase in the breaking strength with an increase in the rate of extension. So next is the rate of loading and time to break. This is usually maintained at 20 seconds as per ISO for the CRL type instruments and not for CRT type instruments. So we'll see this rate of extension and loading and influence of time to break with few problems at a later stage. Now, just understand that with the increase in rate of extension, there will be the strength reading might be shown as higher. Next is the previous history of the sample. So, if you have already strained the material and it has gone above the yield point, I already said about the yield point. We saw three different methods of finding the yield point. The yield point before which the material is elastic and above which the material is plastic, not in a true actual sense, but more elastic before the yield point and more plastic above the yield point. So this yield point, if you have strained above yield point, then it may not regain. as we said already, it will not regain since it is plastic type. Uh, it will not, the secondary bonds inside the polymer chains are breaking, hence it will not regain. So if you test the same material again for a tensile test, then you may not get the actual breaking point again. You have not broken the specimen, because if you have broken the specimen, then you can't test it again. If you have not broken, but you have already strained to some extent, that is usually above yield point, then it will definitely show a different result if you come and test it again. Next is the temperature, the influence of the atmospheric conditions, especially temperature and RH. Temperature and RH, if you, especially the man-made fibers, in which you have the synthetic polymers, they are affected by temperature, and very high temperatures causes some degradation, and even in the TG there is above the TG there will be slight movement in the polymer chain. So that will have an influence on your tensile test results, as the molecules are the factors which give the which actually holds the specimen or withstands the stresses that are created. So if there is a change due to the molecular arrangement due to temperature changes, then that will reflect in your tensile test results. And also the RH. RH is the atmospheric humidity. The textile materials absorb the atmospheric humidity. So when it absorbs the moisture in the atmosphere, if there is more moisture in the atmosphere than the sample, then it will absorb, and it will show, if it is cotton, it will show a higher tensile test result, and if it is a viscose, it will show a lower tensile test result. So the influence of RH and temperature are usually neglected by maintaining a constant temperature along the various testing centers, and also conditioning the sample for some time in that, in 20 degrees centigrade and 65% RH. Whereas in India, we use 27 degrees centigrade and 65 plus or minus 5% RH. So the next one is the type of jaw and clamping problems. So as I said, we are going to hold. So how long, if you, how big is the jaw? How, what is the size of the jaw? How much frictional contact with the fiber or material is having with the jaw? And what is the area of the jaw? So these things have, what is the material type, all those things influence your holding, and which influence your tensile test readings. So you have to always have different clamps for fiber, yarn, and fabric. So fabric clamps will be very higher, whereas fiber clamps will be very small. The yarn clamps should hold like this. So the clamps are different for fiber, yarn, or fabric. And in the jaws, there should not be any slippage. The pressure applied should be very uniform. And if your pressure is very high, then it may damage the sample. If your pressure is low, then it will slip and come, and it may show as an elongation reading in the yarn test usually. So you have to be very careful in the pressure applied and the type of jaw that you are holding. Next is the capacity of the instrument. As I already said, if I have to weigh myself, I can't go stand in a micro balance, or I should not go stand in a weigh bridge. So you have to choose your exact capacity instrument. So for a so the same instrument, the load bearing capacity of that load cell should be sufficient for a fiber. So if it is a single fiber, then 1 Newton is enough for the fiber. And if you have to, you should not go for 100 kilonewton machine. If you're going to weigh a small sample fiber, you have to, a bunch of fiber, 100 grams of fiber, you can go for a 250-gram balance. You know, should not go for a micro balance which weighs 100 microns, or you should not go for a 10-ton weigh bridge to weigh the fiber. So you have to choose a suitable instrument. If it is a weak specimen, weak capacity instrument, and if it is a high strength material, a high capacity instrument have to be chosen. So now we'll go into the principles behind the tensile test instrument in detail, so that we can understand how we will get a better knowledge on the loading, the extension, and the traverse principles. We'll see one by one in detail. So CRL is constant rate of loading, CRE is constant rate of extension, and CRT is constant rate of traverse. Now we'll see this with the diagram. So first let us understand CRE. So we have a fixed jaw here. You have a fixed jaw here. So you are placing a sample. Next, so this is the jaw J1. Maybe we have marked the jaw J1. Next is jaw J2. You have, I have just put a line that it will not look like this, but this is a representation, jaw J2. So the jaw J1 is fixed. That is why you have this markings here. This indicates that the jaw is fixed. So now you are applying load in J2. You are extending J2. You are moving J2 at a constant rate. You are not applying load. You are moving. Here extension causes loading here. So there is a fixed in this thing. You may have a strain gauge which is fixed here. Strain gauge, I hope you all have studied in your 12th standard. I want you to go see what is strain gauge and come back. We will see that in detail at a later session. So there may be a strain gauge at J1 to measure the load that is applied on this specimen. Next, so this J2 may be moving, may be connected to a screw mechanism. You can be connecting it to a screw mechanism, or connecting to, which is connected to a motor, or directly. So screw mechanism may be operated manually or to a motor. So this is how you applied the extension to the specimen, which causes stress in the specimen. This is called as constant rate of extension. J1 is fixed, J2 moves at a constant rate. Usually this is 300 mm per minute. So this is called as constant rate of extension. This is constant rate of extension. Next we'll see on constant rate of traverse. So in constant rate of extension and in constant rate of traverse, the bottom jaw similar. There is a similar arrangement of bottom jaw. The bottom jaw moves at a constant rate. It may be attached to a screw mechanism, in turn attached to a motor, or a screw mechanism attached to some physical moving attachment which moves at a constant rate. So the bottom jaw looks similar. Next, we have the top jaw, but the top jaw J1 is not fixed, whereas it is hanging over a pulley. So you could have seen in a well there is a pulley. Similarly, you in a well you have a rope and tied on the other end. You pull it and it comes. Similarly, a pulley is there. So the pulley the J2 is hanging over a pulley. On the other side, there may be a arrangement which measures the load. So this jaw J1 is not fixed, whereas it is hanging. There may be steel tape attached to a pulley so that it is not fixed, and there may be slight movement which may not be perceivable for our eyes, but there may be slight movement. Hence, the specimen does not have a constant rate of extension. There is no constant rate of extension in the sample, no constant rate of loading also. Just the bottom jaw traverses at a constant rate. Bottom jaw traverses or moves at a constant rate. This is called as constant rate of traverse. So the bottom the difference between extension and traverse, you have the bottom jaw moving at a constant rate in both the cases, whereas the top jaw is fixed in constant rate of extension, and in the top jaw is hanging over a pulley in the constant rate of traverse instrument. So by seeing the instrument, you can easily identify if there is a pulley arrangement for the load measurement. Then It is a constant rate of traverse equipment. So this is simply written as CRE on the left hand side and the CRT principle on the right hand side. Now let us try to understand CRL. We have seen in this we can see the three principles simultaneously. The first one we already saw CRE, wherein dx by dt is constant. X is the extension. So rate of change of extension is constant. Dx by dt is constant. Change x is extension, t is time. So with change in time, the change in specimen length is remains constant. In constant rate of traverse, I said in the bottom jaw J2 moves at a constant rate. Neither dx by dt nor df by dt is constant. Both are not constants in CRT type, whereas in CRL type df by dt is constant. The jaw J2 does not move at a constant rate, but the force applied on J2 remains constant and J1 is fixed. This is a representation of the instrument, whereas J1 and J2 look similarly in the instrument also, but the CRL principle, you do not have constant rate of loading principle. You may not look the same picturization in the instrument. And the example for CRL type instrument is stellometer. CRE type is all universal testers. CRT type instruments, you have your pulley based instruments available in Lee strength for single yarn strength is there. For CRE, you have fabric yarn and Lee testers, all are available for CRE also. So hope you have understood the principles behind the working of the instrument. In each instrument, when we discuss in detail, we will see the principles again. Okay, thank you.